Hello and welcome to our next module on BCH codes. Let's start with a quick outline. We will look at some mathematical preliminaries. We'll start with the primitive polynomial. We'll talk about the construction of extension field. Then we will talk about minimal polynomials, and finally we'll use all of these mathematical tools that we have discussed to form the generator polynomial for BCH codes. So let's do a quick recap as to what we have done already. We have looked at linear block codes, which were putting certain algebraic constraints and enabled us to detect and then correct errors. A subclass of linear block codes were cyclic codes. We had additional algebraic constraints which made them much stronger codes in terms of error detection and even correction. We looked at certain types of cyclic codes and we looked at the circuit implementation. What we want to do today is to look at yet another subclass of cyclic codes called the BCH codes. So, if you remember the cyclic codes, right, they formed a subclass of this linear block codes. Now, we are moving within the domains of cyclic codes. So, BCH codes are a subclass of cyclic codes and are known for their multiple error correcting ability. We will see that very good BCH codes, which stands for Bose-Chaudhary-Hocquenghem codes, are over non-binary fields. So, we have GFQ over which BCH codes are defined, and they can correct several errors, burst errors, and are pretty strong in their error correcting capability. So, if we go to a subclassification, we find that BCH codes form a subclass of cyclic codes. So, linear block codes, we developed a rich theory, then we went to cyclic codes, again more theory to use cyclic codes in terms of polynomial representation, and then we will have BCH codes. We can use the techniques already developed for LBC, cyclic codes, all are applicable for BCH codes. So, let us have a quick introduction. What is so different? If there is a subclass, we need to ask ourselves what are we getting which is more than what we have studied so far. So, the approach is slightly different. So far our approach has been to first construct a code, then find out the distance properties, and based on that find out the error correcting capability. That has been our sequence. In this class of codes, we start from the other end, because at the end of the day we need to tell what is the error correcting capability. In our earlier strategy, error correcting capability came at the end. We will start from how many errors would we like to correct. So, we begin by specifying the number of random errors we desire the code to correct, and then we go on to finding the generator polynomial for the cyclic code. As mentioned before, BCH forms a subclass of cyclic codes. So, we will still have to factorize x raised by n minus 1. But what we will see is that for certain special values of this n, factorization becomes much more easier. And for that, we need to introduce this concept of primitive element. So, what is a primitive element? A primitive element of GFQ. So, if you remember, Galois field with q elements may have at least one element alpha, such that every field element except of course the 0 element can be expressed as a power of alpha. If I can do that, then I can say that alpha is a primitive element. Please note, what is a power? So, a squared is a multiplied with itself. Of course, multiplication is a defined operation over fields. So, a squared is defined, a cubed, and so on and so forth. Let us do a very quick example. Let us talk about GF5. Now, 5 is a prime number. So, Galois field exists and modulo arithmetic will also work. Now, let us say the elements of this field are 0, 1, 2, 3, 4. So, consider the element 2. Now let us look at all the powers of this element 2. So 2 raised power 0 is of course 1, 2 raised power 1 is 2, and so forth. I get the powers as another field element, and once I raise it, I can see that all the 4 elements other than the 0 element can be represented as some power of 2. Therefore, by definition, this number 2, which element 2, is a primitive element. So 2 is a primitive element of the field GF5. Let us look at yet another example over GF5. Let us take the element 3. Now 3 raised power 0 is 1, 3 raised power 1 is 3, and so forth, and once again we are pleasantly surprised to see that all the 4 elements other than 0 are represented as some power of 3. Consequently, 3 is also designated as one of the primitive elements of GF5. But are we lucky? Do we have more? Well, we can try out that all the other elements 1, 4 and 0 are not really the primitive elements. Now we go to another definition of primitive polynomial. A primitive polynomial p of x over GFQ is a prime polynomial. So we already know what is a prime polynomial. You cannot have factors and it is monic over GFQ with the property that in the extension field constructed modulo p of x, we have studied that you can construct an extension field using a prime polynomial. But the property here is that the extension field constructed modulo p of x, the field element represented by x is a primitive element. So under this condition, you have the polynomial p of x is a primitive polynomial. Please note, primitive polynomials of every degree exist over every Galois field. And since this is the definition, a primitive polynomial can easily be used to construct an extension field. Let us look at an example because the definition was slightly convoluted. So let us construct GF8 using the primitive polynomial Px is equal to x cubed plus x plus 1. You can check that it is a prime polynomial over GF2, okay, and we wish to construct the extension field GF8. So let us say alpha is my primitive element. We know that every Galois field has at least one. So let alpha be that one designated primitive element. Then we can represent all the elements of G of 8 by the powers of alpha taken modulo p of x. So let us try that. Say alpha raised power 1 is designated as using this indeterminate z, alpha squared is z squared, alpha cube. Now, so if you have to take alpha cube, then we have to take modulo x cubed plus x plus 1. So if you just look at the working, you have alpha raised power 1 is z, alpha squared goes as z squared, alpha cube goes as z cube, but everything is modulo your px. Now px happens to be z cube plus z plus 1. So if you take z cube modulo z cube plus z plus 1, if you divide it, you get equal to z plus 1. Similarly, alpha raised power 4, because alpha is a primitive element, so I hope it will generate each and every element of the extension field. So alpha 4 is represented as s power 4, and if you again take it as modulo z cubed plus z plus 1, then you can get nothing but z squared plus 1. And I can do this mechanically, alpha raised power 5, and I will get z squared plus z plus 1. I can do alpha 6, I will get z squared plus 1, and if I do alpha 7, well, you will magically get it as 1, and I can keep raising it to the power, and again I go back here. So, other than 0, I have been able to generate all the elements. So, these are all the elements of GF8. Not only are the elements available to us, we in the process have also constructed the addition and multiplication table, and alpha is my primitive element. Why? Because right in front of eyes we have generated, using all the powers of alpha, all the elements of GF8. So, we have actually constructed GF8. After all, what is a field? Field is a collection of elements with the associated addition table and multiplication table. So, we come back to our slide and we pose to ourselves the fundamental question of factorizing x raised to the power n minus 1. But before we do that, what we want to do is would like to say that my n is represented as q minus 1 right now. Okay. So, let B1, beta 1, beta 2 and so on and so forth be the non-zero field elements of GFQ. Then what we would like to do is we want to express x raised to the q minus 1 minus 1. So, please note this is your n, because at the bottom of the calculations we wish to factorize x raised to the n minus 1. That is our primary motivation. So, all this math is being done to have a very efficient, quick way to factorize x raised to the n minus 1. So, we can write x raised to the q minus 1 minus 1 as x minus beta 1, x minus beta 2, so on and so forth up to x minus beta q minus 1. So, there is a simple proof that we can write it like this. So, please note that beta is an element of the extension field. So, since beta is an element of the extension field, it can be represented as some primitive element alpha raised to the power r for some integer r, because every non-zero element in the extension field can be represented as the power of the primitive element. So, beta raised to the q minus 1 you can write as alpha raised to r into q minus 1, and then you interchange these exponents, and then alpha raised to the q minus 1, if you remember, will go back to 1 unity. We saw that case repeat, and then 1 raised to the r is 1. Clearly, therefore, this is a factor, because here I am talking about x raised to the q minus 1 minus 1. So, beta is a 0 of x raised to the q minus 1 minus 1, and this is true for any non-zero element beta, because we have shown for general. So, for beta 1, beta 2, beta 3, this is true. So, I put together all these elements, non-zero elements, multiply them out, and we have a factor. Now, this immediately tells us that I can factorize a polynomial x raised to the q minus 1 minus 1, provided this q is such that the Galois field exists. So, we have an immediate factorization available. So far we were struggling, but here we have right in front of us these linear factors. Let us take a simple example. Let us take GF5, which is a Galois field with 5 element. So, we look at the non-zero elements 1, 2, 3, 4, because we are leaving out 0 here. Therefore, without making any effort, we can immediately write the factors of x raised to the 4 minus 1. Please note q minus 1. What is q? Q is 5, GFQ, GF5. So, we have x raised to the q minus 1 shows x raised to the 4 minus 1. So, if I were to factorize x raised to the 4 minus 1, without doing any effort I can write it as x minus 1, x minus 2, x minus 3, x minus 4, the product of these. Why? Because I have covered all the non-zero elements of the extension this Galois field. So, we now try to connect this to our factorization problem, because please note we are still in the domain of cyclic codes of block length n, and our whole and sole purpose is to factorize x raised by n minus 1. So, we can always write x raised by n minus 1 as some product of its prime p prime factors. Okay, I really do not know how many p's will be there, but there will be these prime factors, and we remember that any factor of x raised by n minus 1 is a potential generator polynomial gx of a cyclic code. So, if you can see that for these p factors there is 2 raised to p minus 2 different non-trivial codes, because for example 1 f1x, f2x, f3x, so on and so forth are individually, then f1x, f2x, f2x into f3x, they are also factors, then f1x into f2x into f3x, f2x into f3x into f4x. So, you take 3 at a time, then 4 at a time, and 5 at a time, till all of them at a time. So, if you add them up, you can get 2 raised to p minus 2, because 1 is a factor and x raised to n minus 1 is also a factor. So, if you remove these two trivial cases, you are left with 2 raised to p minus 2 non-trivial cyclic codes. And what we will try to do is, for special values of n, we will be able to write these factors out completely, and that is the aim of today's lecture. So, this n is critical, and we define this special n for which factorization will be extremely easy as the primitive block length equal to q raised by m minus 1 if I am working over GFQ. So, please note, right in the beginning we are saying that we are willing to work with non-binary codes. So, it is not necessarily GF2, yes, GF2 will be also acceptable, but in general for GFQ let us talk about a primitive block length n equal to q raised by m minus 1. So, please note, for all BCH codes the starting point is a block length which probably has to be a primitive block length. So, a cyclic code over GFQ with primitive block length is called a primitive cyclic code. Now, we would like to work a little bit more on the extension of the factorization part, and so let us say that GF q raised by m is an extension field of GFQ. So, q is a prime number, q raised by m prime power is also an extension field, it has to be a Galois field by definition. So, GF q raised by m is an extension field of GFQ. So, GF4 is an extension field of GF2, GF16 is an extension field of GF2, GF9 is an extension field of GF3, and so on and so forth. Now, let us start with the primitive block length n given by q raised by m minus 1, where m is some integer. So, we have now our basic aim to factorize x raised by n minus 1, but my n happens to be of a primitive block length q raised by m minus 1. So, I substitute the n here. So, I am now in the business of factorizing x raised by q raised by m minus 1 minus 1, and let us say we have these p factors. Okay. So, what we would like to do is we have to choose a finite number of these factors in order to satisfy the distance criteria we need to work with. So, what we do is we observe that every non-zero element of this extension field is a 0 of x raised by q m minus 1 minus 1, we just now saw that, right. So, we can just write x raised by q m minus 1 as the product, the linear factors x minus bj, j being all the non-zero elements of the extension field. We have just seen that. So, this can be written, and bj ranges over all the non-zero elements of this extension field. We had just done this example. Now, this implies that each of the polynomials f I x can be represented in GFQM as a product of some of the linear terms. Please go back and see where we are going. We are trying to factorize x raised to the power qm minus 1 minus 1. Now, there is an easy factorization available here in terms of the product of the linear factors x minus bj's, bj being the non-zero elements, right. Now, what we would like to do is we would like to have the polynomials fi, which were the factors of my x raised to the power qm minus 1 minus 1, are some combination of these linear factors, okay, and bj is a 0 of exactly one of the fix. Now, this fix is called the minimal polynomial of bj, all right. So, it is very clear from this. So, a combination of that will be the minimal polynomial. The smallest degree polynomial with coefficients in the base field, okay, but has a 0 in the extension field. Why? Because bj's are the elements of the extension field, is called the minimal polynomial bj. Let us look at a quick example. Suppose the subfield is gf2 and the extension field is 2 raised to the power 3 gf8. So, consequently, my q is 2 and m, the integer m, is 3. Now, I want to factorize x raised to the power qm minus 1 minus 1. Please note, this is my primitive block length n equal to q raised to the power m minus 1, but q happens to be 2, m happens to be 3. So, q raised to the power m minus 1 is 7. So, I am trying to factorize x raised to the power 7 minus 1 over this field gf8. Now, without worrying too much, I can always write, if 1, 2, 3, 4, 5, 6, 7 are the non-zero elements of gf8, I can always write x raised to the 7 minus 1 as x minus 1 into x minus 2 into x minus 3 and so on and so forth, right. But we have a parallel factorization available. So, please note that if you look at the construction of GF8 using the primitive elements, you have the elements of GF8 written as the 8, these are the 8 polynomials which are the elements of GF8. So, whenever we have these are non-zero elements, we can always write the factorization of x raised to the power 7 minus 1 as x minus beta 1 times x minus beta 2 times x minus beta 3 and so on and so forth up to x minus beta 7. So, this is exactly what it is written. If you see, there are 1, 2, 3, 4, 5, 6, 7 non-zero elements, right? And then you can expand it out and you can see that clearly x cubed plus x plus 1 is some of these elements and x cubed plus x square plus 1 is the other 3 of this element, right. So, let us analyze it a little further. So, what are we trying to do? We have this very clear x raised to the power q m minus 1, this is my n minus 1. So, we are actually trying to work with cyclic codes, where our starting point is always to factorize this. Now, over GF8, I can always factorize it if my elements were x minus 1, x minus 2 to x minus 7. But we can also write the elements of GF8 using polynomials, and we have our polynomials if you construct, and we have done an example before. So, we can write x minus 1, x minus the second element is z, x minus z squared, x minus z square minus 1, because z square plus 1 is a polynomial, and we have again product x minus z square minus z, then we have x minus z square minus z minus 1, and then you can have 1, 2, 3, 4, 5, 6 of them are there, and then 0 is not being included. So, what is important is to observe that x minus z, x minus z squared and x minus z square minus z, right. These are together, when you multiply them out, they form x cubed plus x plus 1, right. And if you look at x minus z minus 1, so that is one element is missing, right. So, if you look at x minus z minus 1, and then you look at x minus z square minus 1, and if you look at all the x minus z square minus z minus 1, these two, if you multiply them out, they form x cubed plus x square plus 1, and you already have x minus 1 as coming from here, and this is your x raised to the power 7 minus 1. So, it is a matter of visualizing that this linear factors could be written immediately without even thinking, but when you start clubbing together, you can get them in terms of the factors with coefficients in the base field. So, please note that each of these polynomials have a coefficient either a 0 or a 1. So, they belong to GF2. This is important. So, the coefficients of this polynomial, look at the number of z's. So, if I take x minus z into x minus z square into x minus z square minus z, so many z's, but you multiply them out, magically all the z's would cancel out, because z belongs to the extension field, but here the coefficients are only in the base field GF2. Same with this guy. So, it is very easy to factorize this x raised to the 7 minus 1 like this. Okay. So, we come back to our slides and we say time for some observations. So, if you look at x raised to the power 7 minus 1 in the slide, you have, as we have written out, x minus 1 into x cubed plus x plus 1 into x cubed plus x squared plus 1. Now, we can write out the table and we see that the multiplication and additions are carried out over GF8, and we talk about these three minimal polynomials. Please note that minimal polynomials, if you look at the definition, the smallest degree polynomial with coefficients in the base field. So, this is what we highlighted. Each and every minimal polynomial has the coefficients in the base field, but at the same time 0 in the extension field, which is obvious because it is a product of the linear factors like this. So, zeros in the extension field, and you have the elements which correspond to the zeros are given by these BJs. So, for the first case, it is product of x minus z, x minus z square, x minus z square minus z. So, these are the three elements in the extension field, and the other three elements again in the extension field correspond to this minimal polynomial. Now, we make a startling observation. If you look at elements being represented as powers of alpha, we note a pattern here: alpha 1, alpha raised to power 2 and then alpha raised to power 4. Here alpha cubed, alpha 6, alpha 12. Well, alpha 12 will go back into alpha 7 into alpha 5, and alpha 7 is always 1, alpha raised to power 7 is always 1 for GF8. So, it is alpha 5 here. So, the observation is in the pattern that the minimal polynomial x cubed plus x plus 1 corresponds to alpha, alpha squared, alpha 4, whereas x cubed plus 1 corresponds to cubed 6 and alpha 12. So, maybe things are going to be much easier. I do not even have to worry which one to take if I can just observe that the pattern. Please note the element and powers of alpha have a 1-to-1 correspondence because alpha is the primitive element. So, we have made this observation that the elements are the roots of a minimal polynomial in the extension field which have the type beta raised to a q r minus 1, where beta is an element of the extension field, right. So, if alpha if you want to write alpha as the primitive element, it is alpha raised to a q r minus 1. What is q? Q was 2, r was 3. So, we can always write in terms of alpha raised to power 2 raised to power 3 minus 1. Now, two elements of GFQM that share the same minimal polynomial over GFQ are called the conjugates with respect to GFQ. For example, you have seen that alpha raised to power 1, alpha raised to power 2, alpha raised to power 4 have the same minimal polynomial, right. Similarly, we had seen in the previous slide that alpha cubed, alpha 6, alpha 12 share the same minimal polynomials. So, they are also conjugates. So, fx, if fx is the minimal polynomial of beta, then it is also the minimal polynomial of the elements of the set beta raised to q. So, since beta was earlier there, then beta squared and then beta 4 and so on and so forth up to beta raised to q r minus 1, where r is the smallest integer such that beta q raised to r minus 1 is equal to beta, and this is called the set of conjugates. So, in the earlier example, alpha, alpha squared, alpha raised to 4 were the set of conjugates. So, now we make our lives even more simpler. The minimal polynomial of beta can simply be written as x minus beta, x minus beta q, x minus beta q squared and so on and so forth up to x minus beta q raised to r minus 1. So, let us look at a simple example. Consider GF 256. Now, if you try to do this by the standard technique, you may have to work a little harder, but GF 256 as an extension field of 2 is can be easily factorized. So, suppose I want to look at alpha being the primitive element of GF 2 raised to 56. So, without even worrying too much, I can say, oh sure, the first set of conjugates I can write as alpha, alpha squared, alpha 4, alpha 8, 16 up to alpha 128, right. So, you can do a check that alpha 256 could have been the next element, but 256 is raised to alpha q minus 1. Now, alpha raised to q minus 1 is always unity. So, alpha 255 is 1 into 1, so alpha 1. So, then it will start repeating cyclically. So, we terminate our search beyond this point. So, what is the minimal polynomial of alpha? Well, straight away without any sweat, x minus alpha squared, x minus alpha 4, x minus alpha 8, so on and so forth up to x minus alpha raised to 128. Now, what about, so alpha and alpha squared are covered, alpha cubed is not covered. See, we went to alpha, alpha squared, alpha cubed is not covered. So, what will be the minimal polynomial for alpha cubed? Well, alpha cube, alpha 6, alpha 12, alpha 24, so on and so forth till alpha 129 and so on and so forth. And please note that if you have to factorize x raised to the power n minus 1, where n is a primitive block length, then I need to have all of the alphas in business. So, let us look at what we are trying to say here. So, if you look at factorizing x raised to the power n minus 1, right, in this example q is equal to 2, right, and so we have m. So, m is equal to suppose 8. So, we have 2 raised to the power 8 as 256. So, if you have to factorize this, all you have to do is you can keep writing till you have x raised to the power alpha raised to the power 1 256. So, 255, and that is it. We have immediately written all the factors. Now, if you have to write it out in terms of minimal polynomial, all you have to do is choose the right candidates. So, alpha, alpha square, alpha 4, alpha 8 somewhere, alpha 16 and so on and so forth. You choose the right candidate and you get the first set of. So, you get x minus alpha, x minus alpha squared, x minus alpha 4, x minus alpha 128. Now, if you multiply them out, all the alphas will disappear, because your base field is GF2 and you will be left with some big polynomial with coefficients either 0 or 1. But we have just regrouped. Now, we have not exhausted, so multiplied by, and then we have x minus alpha cubed is missing. So, alpha cube, x minus alpha 6, x minus alpha 12 and keep going till x minus alpha 129. And then you have actually exhausted some of the other ones, right. And then you have 1, 2, 3, 4, maybe 5 is not there, because 5s are not coming. So, you have got x minus alpha 5, then x minus alpha 10 and so on. So, you get till we exhaust all of them. So, 5 we start exhausting, and finally, we will exhaust all of these factors, and we will write the factorization in terms of the minimal polynomial. So, this first guy, this first product will be your f1x, this will be your f2x and so on and so forth. So, this what are we trying to do? We are trying to factorize this xn, and hopefully these guys would lead to me the generator polynomial. So, my final aim is to get g of x, and that is all we need for cyclic codes. So, we go back to our slide and we go back to our BCH codes. So, BCH codes defined over GFQ with block length q raised by m minus 1 are called primitive BCH codes, and why this primitive block length is important is because it can help us factorize very easily. So, factorizing x raised by n minus 1, that has been a job right from the beginning. We know that gx is a factor of x raised by n minus 1. Therefore, the generator polynomial of a cyclic code can be written in the form gx is equal to LCM of f1x, f2x up to fpx, where f1x, f2x are the minimal polynomials of the zeros of g of x. Okay? So, now we have suddenly we have gotten this product in terms of the minimal polynomials. We did this example just now. But what is great is each minimal polynomial corresponds to a 0 of g of x in the extension field. Okay? So, we will design good codes with desirable zeros using this approach. So, our approach is in terms of designing g of x. Okay? We are now in the business of designing g of x by choosing appropriate minimal polynomials. So, let us look at very quickly how things will work, and you will see the logic very quickly. Let c of x be a code word polynomial and ex be an error polynomial. Then the received vector is always a polynomial representation Vx is equal to Cx plus Ex, where the polynomial coefficients are over Gfq. Now, we look at the extension field Gfq raised by m. Let G1, G2 up to Gp be those elements of Gfq raised by m which are the zeros of g of x, that is g of gi is 0. Now, why do we need that? Well, Cx is some polynomial a of x into g of x. So, if gi is a 0 of g like this, then gi must be a 0 of c. Therefore, the received new gi is nothing but cgi plus egi, but cgi is 0 is nothing but egi, very similar to the syndrome version that we decided to do even for linear block codes and cyclic codes. So, now we have a block length n, and we have got now new gamma I is nothing but, this is the polynomial representation e j gamma I j. So, eventually we have a set of p equations that involve components of the error patterns only, is the syndrome. So, now we have a system of equations. If it is possible to solve the set of equations for Ej, the error pattern can be precisely determined, because we are in the business of error correction. So, whether this set of equations can be solved depends on the value of p, that is the number of zeros of g of x. So, therefore, in order to solve the error pattern, we must choose a set of p equations properly. So, now let us move to our attention towards trying to design a t error correcting code. How many equations do we need to correct t errors? Okay. So, let us define the syndrome. Si is nothing but error polynomial of gi. So, we define that. So, we wish to choose the zeros g1, g2 up to gp in such a manner that t errors can be computed from s1, s2 up to sp. So, if alpha is a primitive element, then the sets of gi which allow the correction of t errors are simply alpha raised by 1, alpha raised by 2, alpha q up to 2t. Okay. So, it clearly shows that I have enough equations to now determine the error pattern uniquely. Okay. Suddenly, we have a handle. If we need to correct more errors, we need to have more equations. So, then it tells us a very simple way to get the generator polynomial for BCH codes. So, first starting point is that the primitive block length should be honored. So, n must be q raised by m minus 1. Then all the theory that we have developed holds good. So, we choose a prime polynomial of degree m and construct GFQM. It is now very easy. So, the first thing is that you need a prime polynomial which will be the primitive polynomial, which will be used to construct the extension field. Then find the minimal polynomials for alpha raised by I, where I is equal to 1, 2 up to 2t. Please note that by now we are very comfortable finding the minimal polynomials, because we know how to make the set of conjugates. And then the g of x, the generator polynomial, is simply given by LCM of f1x, f2x and so on and so forth. Why LCM? Because sometimes f1x and f2x will be the same. It depends on your Galois field, but you don't want to repeat it because Gx is of the lowest degree, therefore we take that LCM. So, we have now a very simple way for finding a T error correcting code. So, starting point is N and T. You tell me how many errors you want me to correct and you tell me the primitive block length. With that, I will give you a BCH code which will guarantee you to correct at least T number of errors. So, please note, code designed in this manner can correct at least T errors. Therefore, it is called the designed distance D, which is equal to 2t plus 1, and sometimes it is greater than the minimum distance. And it goes without saying that the generator polynomial has a degree n minus k. So, we started with n and t, and then we decided how many minimal polynomials to pick up, and then k comes automatically. So, k gets decided later on. First we find out n and then t and then k. So, once we fix n and t, we can determine the generator polynomial of the BCH codes. So, we now come to the conclusions for today's lecture. What have we studied today? We started off with primitive polynomials, and then we learnt how to create an extension field. Then we studied minimal polynomials, and finally our final result of how to determine the generator polynomials for BCH codes. With that, we come to the end of this lecture.